Hi, today we're going to be working on Taylor polynomials and approximations. Our essential questions for today is how can we approximate the value of a function using a Taylor polynomial? So what is a polynomial approximation? Our goal of it is to find a polynomial that we call p of x that's going to approximate our function f of x. So we're going to find a c value such that the polynomial and the function are equal at that point. So the polynomial and the function have to touch at least once. So for example, a tangent line would be a linear approximation. Okay, in a better approximation, they would have the same slope, so similar to a tangent line. Okay, p prime of x would equal, or c at the point would equal f prime of c. So it's not that they would be equal everywhere, it's that they would be equal at least at that one point. Now, the difference from a tangent line is that a tangent line is only a linear approximation. It only goes to the first degree, which on a curve makes it not very accurate. It only touches once. If I was to have a higher degree polynomial, I could hug my curve a little more and be a little more accurate than just a tangent line. So this polynomial we would say is centered at C. And so on the picture, you can see that we have p of c and we have p prime of c, and that the two of them are touching at c. And so the f is our one in black, and then p is the one in gray. So this one is a tangent line approximation, but we will look at higher degree ones later on. So now we want to find a first degree polynomial. So we're going to use f of x equals e to the x. We're going to find a first degree polynomial. So we're going to do a naught plus a1x. So basically mx plus b, right? Whose values and slope agree with f at x equals 0. So we're trying to center it about 0. So I'm going to go ahead and I'm going to find what f of 0 is. Oops. So f of 0, that does not look fantastic. Let me see if I can adjust this a little bit. All right. So f of 0 is e to the 0, which is 1. So that means my polynomial, I need p1 of 0 to equal 1. So now we're going to be constructing a table comparing the values of p3 of x. Now p3 of x, this is called a third degree polynomial. So that 3 means this is going to go up to a power of 3. So if you're looking at the polynomial, notice that the highest degree is x cubed. And so we're doing it for the function of e to the x. And we're going to look at values near 0 to see how accurate is this polynomial. So what I'm going to do, you guys should grab your TI Inspires, and you should be inputting this in with your TI Inspire. I'm going to go ahead and use a Desmos. I'm going to use Desmos to be able to create my tables. So you guys go ahead and grab your Inspires, pause, start typing those in. So right here I have e to the x, and then my other one is 1 plus x plus 1/2 x squared plus 1 over 3 factorial x cubed. And what I'm going to go ahead and do is change the colors just so you can see the two different equations. So notice e to the x right there is being hugged by my polynomial approximation. So for a long stretch over here, it's almost the same function, but then it separates off here, and then you can see as we get higher, it starts separating. So what I'm going to do right now is I'm going to change this to a table and put in our table values. And we're going to compare the table values to see how accurate it is. So my table values are -1, -0.2, -0.1, 0, 0.1, 0.2 and 1. And now I'm going to compare it to the table on this one. So I'm going to hit my gear, table. I'm going to put in the same table values, and we're going to compare and see how close is the approximation. All right, so looking at our tables, if you look at -1, they're close, but they're off by about 3,000ths, or 300ths, sorry. They're off by about 300ths. If we go to -0.2, now they've gotten closer. Now they're off by, about a 10,000th. All right. Then you get to -0.1, and now they're only separating at, what is that? Way off here. Okay. At 0, they're exactly the same. 0.1, again, very, very close. And then it gradually gets further apart. So notice my polynomial is a very good approximation on this small interval. But if I went beyond this interval, it would not be as accurate. Yes.
Okay, so
right.
So that's the second one. Like that's number 6. So I think it's turning to the.
So if n has derivatives at c, then we have this polynomial that is the function value at c plus the first derivative at that c number, x minus c, plus the second derivative over 2 factorial, x minus that number squared. And it goes on to the nth derivative over n factorial, x minus c to the n. So we always end at whatever degree derivative we're looking for. C is going to be some number. So it's whatever number we are centered around. And so this is called an nth Taylor polynomial for f at c. All right. Now, if c is centered around 0, this is now called a Maclaurin. This is called a Maclaurin polynomial. And so Maclaurin is just a special case of a Taylor polynomial. So for that, we have f of 0 plus the first derivative of 0 times x plus the second derivative of 0, x squared. All right, and so this becomes my Maclaurin. Your notes had a typo. So instead of Taylor, your notes say Taylor. Instead of that, it should say Maclaurin. So please adjust your notes to say Maclaurin. So now we're going to find the nth Maclaurin polynomial for f of x equals e to the x. So now that we see that word Maclaurin, we know it's centered around 0. So as soon as you see the word Maclaurin, it suggests we are centered around 0. So we need to know a few things to be able to find this polynomial. We need to know what f of 0 is. We need to know what f prime of 0 is. We need to know what f double prime of 0 is. And we go as far as we need to see a pattern. If we see a pattern, then we can represent that for the nth term. So f of 0 is really straightforward. It's just what is e to the 0, and that's 1. To find f prime of 0, though, you need to know what f prime of x is. So f prime of x equals e to the x. F double prime of x is e to the 2x. Whoa, that is so wrong. Is e to the x. So the great thing about the derivatives of e is they're all the same, which means all of them are e to the 0 is 1. E to the 0 is 1. So we notice a pattern that the derivative will always be 1. So now I'm going to write my polynomial. So for my polynomial, we're doing the polynomial of nth degree. And so I start with f of 0. F of 0 is 1. Okay, plus. Then it's supposed to be f prime of 0 times x. Then it's going to be the second derivative, 1 over 2 factorial, x squared. So we're seeing a pattern here, and that pattern is 1 over n factorial x to the nth power. And this is my nth degree Maclaurin polynomial. This is my nth Maclaurin polynomial. Oh my God. All right, so we're going to be finding the Taylor polynomials, and this time we're doing a Taylor polynomial not a Maclaurin. So it's centered at 1. So that means I'm going to be using the structure of x minus 1 the whole time, of x minus c. So now rather than finding my function at 0, I'm always finding it at 1. So let's start by finding what f of 1 is. ln of 1 is 0. It's good that this is centered around 1, because if we were centered around 0, I could not find ln of 0. My function would not be defined. So f of 1 is ln of 1. And so that gives me my 0-degree polynomial. My 0-degree polynomial only uses f of 1. My 0-degree polynomial only uses f of 1. And f of 1 is 0. So let me clean up that 0 a little bit. There we go. All right, now our second degree polynomial. Why am I skipping to second? I don't know. My first degree polynomial is now going to use that 0 plus my first derivative times x minus 1. So my first derivative of ln is 1 over x. So f prime of 1 equals 1 over 1 is 1. So now I get over here 1 times x minus 1. Then I'm going to find my second derivative. So my second derivative of this function is, you treat that as x to the negative 1. So I get negative 1 x to the negative 2, or negative 1 over x squared. So f double prime of 1 is negative 1. All right, so now for my second degree, I have everything from the first one, but now I have minus 1 over 2 factorial x minus 1 squared. All right, so I'm going to clear some space over here for me. Oops. All right, so now I'm going to find my third derivative. So my third derivative, we're dealing with, remember our second derivative was negative 1 x to the negative 2. So my third derivative is going to be positive 2 x to the negative 3. And so if I plugged 1 into here, I would get 2. So P3, oh, and on all of these I should be saying of x. So P3 of x is, I'm not going to bother writing the 0 anymore. So it's x minus 1 minus 1 over 2 factorial x minus 1 squared. Now I'm on the third degree, so now it's plus 2 over 3 factorial x minus 1 cubed. All right, and so now we have the fourth degree to do. So on the fourth degree, my fourth derivative of x is, now I bring down that negative 3 and I get negative 6 x to the negative 4. So if I plugged in 1 to that, I would get just negative 6. So P4 of x is x minus 1 minus 1 over 2 factorial x minus 1 squared plus 2 over 3 factorial x minus 1 cubed. And then it's minus again, it's negative, so notice this is alternating. So that's negative 6 over, and now it's the fourth degree, so 4 factorial x minus 1 to the fourth. One thing I'm not doing at this point, but could be good and useful at times, is to reduce your fractions. So 2 over 3 factorial would actually reduce to 1/3. Negative 6 over 4 factorial would reduce to negative 1 over 4. So just keep that in mind. All right. And so those are my up to my fourth degree polynomial for ln. Now the next one we're going to be doing Maclaurin. So Maclaurin means we're centered at 0. So if it doesn't tell you what it's centered around and it says the word Maclaurin, we're centered at 0, meaning we will be using x. All right, so I want to find P0. So for P0, I just need f of 0. So f of 0 is cosine of 0. And on the unit circle, 0 occurs on the right, and so that's a point of 1. So that means P naught is 1. Sorry, gotta fix bad habit of not writing of x. P naught of x is 1. My second degree. Well, my second degree will need my first degree as well in there. So let's figure out what f prime is. F prime of x is sine x. But here's the thing, sine x, if I found f prime is 0, sine of 0 is 0. So that's kind of why we're skipping all the odd ones, is because sine's going to make that term go away. Okay, so for example here, when I do my first degree, it's 0 times x. So all the odd degrees are going to go away. So my second derivative, and actually the derivative of cosine is negative sine, but it's still negative 0. So now the derivative of negative sine is negative cosine. So f double prime of 0 is negative 1. So for the second term, it's negative 1 over 2 factorial x squared. All right, so I can rewrite that as just 1 minus 1/2 x squared. All right, now moving on. I'm going to do my third derivative. So the derivative of negative cosine is going to be positive sine. But again, sine's going to be 0, so that's why the third degree is going to go away. So we're going to skip over to the fourth degree. So the fourth derivative, the derivative of sine is cosine. Well, and I know that cosine of 0 is 1. So now I get 1 minus 1/2 x squared plus 1, because the fourth derivative is 1. So again, I'm skipping the third because it's 0. I'm skipping the third because sine of 0 is 0. So I'm over to the fourth. And so the degree and the factorial are always matching. Always matching. All right, so hopefully we're starting to see some pattern happening here. If you see the pattern, you can actually skip to the 6 right now. But if not, my fifth derivative would then be back to negative sine. So my 6 would be negative cosine. And we know that negative cosine of 0 is 1. So, by the way, I just realized I wrote third there when we were doing the fourth. And so now we're skipping again to the 6. So I get 1 minus 1/2 x squared plus 1 over 4 factorial x to the fourth. But now we have minus again. So we have minus 1. So I have minus 1 over, and we're the 6th degree, so 6 factorial x to the 6. So now we're supposed to use it to approximate cosine of 0.1. So what you're going to do is you're just going to plug in 0.1 everywhere there's an x in my 6th degree polynomial. So this approximation is exactly that, an approximation. It's not an exact value. So I would say cosine of 0.1 is approximately P6 of 0.1. And P6 of 0.1 is exactly 1 minus, and I honestly don't want to write this all out by hand. So you can write that all out by hand, but I'm going to go ahead and go into my calculator. I'm going to type it in my calculator and see what I get out. Whatever you get out is going to be your solution of your approximation. So go ahead and practice, type it in your calculator, and compare with each other. Okay, so now we want to find the third degree polynomial for sine. And this time we're going to expand it about pi over 6. So since we're expanding around pi over 6, we're going to have quantity. Let me get my writing tools going. Okay, we'll have to use these ones. X minus pi over 6. So we're going to be expanding around x over minus pi over 6. So now f of pi over 6. So pi over 6, the coordinate pi over 6, that's going to be 1/2. The vertical portion is going to be 1/2. It's a short triangle. So sine of pi over 6 is going to be 1/2. So then f prime of x is cosine x. So f prime of pi over 6, cosine of pi over 6, that's the long side, so that's going to be root 3 over 2. The second derivative is going to be negative sine x. So f double prime of pi over 6 is going to be negative 1/2. And now I need to go to the third degree. So I'm going to add on the third degree. So f third degree of x equals now negative cosine x. So the third derivative at pi over 6 would be negative root 3 over 2. So then to find the third degree polynomial, P3 of x is going to be f of pi over 6, so the actual function, plus the first derivative times x minus pi over 6. So my first derivative was root 3 over 2 times x minus pi over 6. And then it's plus the second derivative. So my second derivative is actually negative 1/2. So it's going to be minus 1/2. But it's supposed to be over 2 factorial. Since it's supposed to be divided by 2 factorial, I'm going to put that 2 factorial in the denominator. And that should be times x minus pi over 6 squared. So that's second degree. I'm to a power of 2 so far, and I didn't give myself enough room. So I'll just continue on another row. Now it would be not plus because the third one is negative as well. So I get negative root 3 over 2. And so this should be over 3 factorial, but I'll put that in the denominator. X minus pi over 6 cubed. And there's my third degree polynomial. All right. We are now going to go to the next slide. So now we want to find a fourth degree polynomial to approximate the value of ln of 1.1. So you actually already found the fourth degree. So what I want you to do, I'd like you guys to try this one, is use your fourth degree that you found a few slides ago. So you found the fourth degree for centered at 1 before. But now we're doing it at the point 1.1. So to do this one, I'm going to say let's go ahead and do this one together. So let's start this one. I'd rather do this with me in front of you explaining. So pause on this one, and we'll go ahead and do this one on Wednesday. So we're going to look at the last slide then. And this one is just a definition. So our polynomials are approximations. They're not exact values. So as a result, there will always be a remainder. We call this remainder r sub n. And so the actual function value, so this is my, f of x is my actual value, is always going to be the approximation, the approximate value, plus some remainder. And so we're going to be dealing to try to figure out a range of where a remainder would be. This would tell me my error range, my error value. So we'll be looking at that a little more later on.